Okay, so the next topic we're going to deal with is integrals involving powers of secant and tangent. So we kind of talked about, or we did last week, talked about ones involving sine and cosine. Whoops, secant and tangent. And so what we were able to do on those was you would let u equal one of them if there was an easy way to get du and then rewrite everything in terms of u. And if that didn't work, then you used half angle formulas. And we had like a quick rule for that where if one of them was odd, you let u equal the other trig function. The same ideas work here, although the rule's not as quick as that. We could come up with cases, I probably won't, but it's easier to think through what's going on. With secant and tangent, we have the relationship that the derivative of tangent is secant squared, and the derivative of secant is secant tangent. And so if u is tangent x, then du obviously is secant squared x dx. And if u is secant x, then du is secant x tangent x dx. And then we have the identity like, so sine squared plus cosine squared is 1. We have a similar identity that 1 plus tangent squared is secant squared. And so that identity lets you rewrite secant in terms of tangent, and it lets you rewrite tangent in terms of secant. And it technically always works, but it's usually only useful for even powers. And so, or at least in integrals, that's the case. So like once we've separated out du, we want the one that we're rewriting to have an even power. And so let's look at an example where we're going to do this. So if we have like the integral, I want to leave some space up here, but let's say I have the integral of, let's do tangent to the third x secant to the third. That's what I want, yeah. All right, so if we do tangent to the third and secant to the third, then the idea is, okay, we want to figure out which approach is going to work. So do I want to let u equal tangent x, or do I want to let u equal secant x? And so if I let u equal secant, du is secant tangent, or secant x tangent x dx. And if I let u equal tangent, du is secant squared x dx. And so let's look quickly through both approaches. If I were to do u equals tangent, then I'm going to rewrite the problem where I leave tangent alone, and then I've got one factor of secant left because I'm going to take two factors of secant for the du. And now from there, which one would I want to rewrite at that stage? So if I'm going to do that, which one do I then need to rewrite? So I need to rewrite the one that's not u. So if I'm going to do this approach, I need to rewrite secant. And the fact that secant has an odd power at that stage, that's bad, because we're going to get a fractional power when we rewrite it. Does that make sense to everybody? Okay, so that being an odd power is bad. If I do u equals secant, then I'm going to rewrite it where I have tangent to the third. I'm sorry, I'm going to have tangent squared and secant squared, because I'm going to take one factor of each. And I'm going to reserve that for the du. And now they both have even powers, which is fine, but the one we care about in this setup is tangent. So this even power, that's good. Up here, the odd power, that's bad. And so the one we want to rewrite after we separate out the du, so after we separate out the du, the one that is not u needs to have an even power. So the fact that tangent has an even power here, that means it's going to work. The fact that secant has an odd power here means that's not going to work well. So everybody get that idea? Is everybody clear? Okay, and so I'm going to erase the stuff that I've got in red because we're not going to actually use that approach. And so we're going to go with this approach where we've got the even power. Now we're going to rewrite tangent in terms of secant, but based on this identity, tangent squared is equal to secant squared minus 1. So I can rewrite this as secant squared x minus 1 times secant squared x times secant x tangent x dx. And now this is the du still. So I've got u squared minus 1 times u squared times du. And now it's relatively straightforward, but does everybody follow it? Any questions to there? Okay, and so the reason it's straightforward is because we can distribute the u squared. We get u to the fourth minus u squared du. That's then 1/5 u to the fifth minus 1/3 u to the third plus c, and u was secant. So we get 1/5 secant to the fifth minus 1/3 secant to the third plus c, and that's the answer. All right, any questions on that? That's good. Okay, so let's try tangent to the fourth, secant to the sixth. All right, so let's think this one through. So again, kind of the two options are to let u equal tangent or let u equal secant. In this case, du is secant squared. In this case, du is secant tangent. Remember, we're not doing like parts. We're just doing u sub, and only one of these two setups is the one that I want to use. So if I let u equal tangent, and maybe some cases both work, and so let's kind of figure that out. But if I let u equal tangent, du is secant squared. I'm going to set aside 2 factors of secant. That's going to leave 4 tangents and 4 secants. And which one would we then have to rewrite? So if u is tangent, we're going to have to rewrite which one?
Secant.
Secant. And so the fact that after separating that, secant would have an even power means that this approach will work. Does that make sense? Okay, let's think through this one just to kind of practice that thinking. So if I were to separate out 1 secant and 1 tangent, that's going to leave 3 tangents and 5 secants. And in that case, we don't care about secant, but the fact that tangent has an odd power, that's bad. So we don't want this setup. We do want the setup on the left. Is everybody clear how to determine that? So it's the same thinking as sine and cosine. It's just there's not a quick way to say it. It's not like, okay, if one of them is odd, let u equal the other. Although you could come up with cases, I think, and probably textbooks do. We're not going to. We're just going to kind of think them through real quick and see which one works. So sometimes one works. Sometimes they both work. Sometimes neither of them work. But we would like one of these two to work. So, okay, so take a minute and see if you can get it from here. So I'll give you a minute to work it, and then I'll start working it on the screen. So take a minute and try it. Okay, so if you're good, keep working, but I'm going to start working it out. So if we're going to use this setup on the left, we're going to separate out 2 factors of secant. That leaves all 4 tangents there. And instead of 6 secants, we're going to have 4 left. Whoops. And then we're going to put 2 of them next to the dx, and we're kind of reserving that for the du. So that part is the du. And now since u is tangent, we're going to rewrite secant in terms of tangent. Well, 1 plus tangent squared is secant squared. So we're going to get 1 plus tangent squared and then squared. And then secant squared x dx. And now that's u to the 4th times 1 plus u squared squared times du at the end of that problem. Not done, but any questions to there? Everybody good? Okay, and so we expand that. So you have to square that first. If you square that, you get 1 plus 2u squared plus u to the 4th. And now we're going to distribute the u to the 4th. So we get u to the 4th plus 2u to the 6th plus u to the 8th du. Make that actually look like a 4. And now you do the power rule in all 3 of those parts. So we get 1/5 u to the 5th plus 2/7 u to the 7th plus 1/9 u to the 9th plus c. And then u was tangent. And that's the answer. All right. Any questions on that? Pretty straightforward. Okay. So I want to try one more, and then I want to kind of talk about it in general. So let's try the problem secant to the 4th x dx. So we're going to go ahead and work this together. If you think you know how to do it, you can ignore me or mute me and then go ahead and do it yourself and check it. But on this problem, even though tangent's not in the problem, it's an option to let u equal tangent. So u equals secant is also an option. If we were to let u equal secant, du is secant tangent. And there's not a good way to get that because there's no tangent here at all. So u equals secant's a bad approach for this problem. U equals tangent is a better approach for this problem because if we let u equal tangent, du is secant squared. And after we separate the secant squared, we've still got secant squared, which is an even power of secant. And now it's easy to rewrite this in terms of tangent. Does that make sense to everybody? All right, and so we rewrite it as 1 plus tangent squared x times secant squared x dx. And now that's 1 plus u squared du. And now that's u plus 1/3 u to the 3rd u to the 3rd plus c. And u is tangent, so we get tangent x plus 1/3 tangent to the 3rd x plus c. All right, and so a little weird that we're letting u equal something that's not in the problem, but we did that last week with sine and cosine as well. All right, any questions so far? I think these are relatively straightforward. Is that true? It's been too bad. All right. Okay, so a couple comments kind of going back through what we've been talking about. So if this at this stage, so like let's say this had been secant to the 8th then this would have been secant to the 6 still, because we're still separating out 2 secants. How would that change this? Would this become a 3? Would this become a 3? Would this not work? Or would something become a 4? So if this is a 6, what changes in this line? What do you guys think? So this becomes a 3. So you'd have 1 plus tangent squared cubed, and this would become a 3. And then you'd have to cube that, which is more annoying. It's a little bit more work, but it's not like that hard. It's something we can still do. Does that make sense to everybody? Okay, and if this had been an 8, this would be a 4. This is still 1 plus tangent squared because of the identity. Okay, so that's one thing to watch for, that, you know, these powers could be bigger. That 2's annoying enough, I guess, but this is, and here it's to the first, but if this was a 4, you know, you'd have it squared, or if this was a 6, you'd have this cubed. Another thing is that when we talk about cosecant and cotangent, almost exactly the same relationships exist. So the derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. And 1 plus cotangent squared is cosecant squared. So those problems can be done if you have powers as cosecant and cotangent. Those problems are done exactly in the same way, except that when you're getting the du's, you need to get negatives in there. So you'd have to have a negative here and a negative out there. But aside from that, they would work almost identically to the problems we've been doing. Okay, so we've got powers of sine and cosine, what we were doing last week, powers of secant and tangent, what we're doing this week, or today so far. Okay, so what we want to do is try to figure out, okay, which approach are we going to use? So what I'm going to do is put a bunch of problems on the screen. And what I'd like to know is what U substitution approach works. So should it be U equals tangent, or should it be U equals secant, or do both of those work, or do neither of those work? And then if it's sine and cosine, I'm going to mix in a few that are sine and cosine. Same question. Should U equal sine? Should U equal cosine? Do both of them work, or do neither of them work? Does that make sense, everybody? Okay, so I'm going to put a bunch on the screen. I'm going to give you a couple minutes to think through what's going on. So which U sub should we use? And again, it's possible that there's more than one option. It's possible there is no good option. And so let's put a bunch up. Let's do secant to the 5th x tangent to the 7th. All right, so go ahead, give you a minute on those. Let's figure out which U sub or which U subs work, or if neither of them work, say that. And then we'll check here in just probably a minute or two. Yeah, somebody asked real quick, could we go up to the identity for cosecant cotangent? The identity for cosecant cotangent is that 1 plus cotangent squared is cosecant squared. That's the one you meant, right? Yeah.
Yeah.
Okay, cool. Just make sure. All right. All right, I'll give you a minute or so, and then we'll talk about them in a minute. All right, so let's start talking about these. So on the first problem, if you let u equal secant, du is secant tangent. So if you let u equal secant, you're going to have 4 secants left and 6 tangents left. Which one do you then have to rewrite if u is secant?
Tangent.
Tangent. And so the fact that there's 6, that's good. So u equals secant works. Okay. If u is tangent, du is secant squared. So you're going to separate out 2 of those. That leaves 3 secants and 7 tangents. If u is tangent, we need secant to then have an even power. It doesn't, so that's not a good approach on this problem. So u should be tangent, and u equals secant does not work. Does everybody understand that thought process? Okay. On the next one, if u is secant, du is 1 secant and 1 tangent. That leaves 3 secants and 4 tangents. That works well because we need to rewrite tangent. And so then u equals secant will work fine. If we let u equal tangent, right? Yeah. If we let u equal tangent, du is secant squared. We separate out 2 secants. That leaves 2 secants and 5 tangents. We don't care about tangent at that point, but the fact that secant is even, that means that's going to work as well because we need to rewrite secant in that case. So both approaches work on problem 2, and you can set up whichever way you think is easier. I think it's probably easier to use tangent because that keeps the power smaller, but it doesn't matter. Does that make sense, everybody? Okay, any questions? All right, so the next one, u equals secant. If we do that, du is secant tangent. That's going to leave 3 tangents and 7 secants. We don't care about secant at that point because u would be secant, but the fact that tangent's odd is bad, and so then u equals secant doesn't work well, does not work well. U equals tangent, du is secant squared. That's going to leave 4 tangents, which we don't care about, but 6 secants, which we do care about. The fact that that's even is good. So u equals tangent is going to work on problem 3. And so please ask if this rationale doesn't make sense. But the idea is you got to think, okay, after you separate out the du, how many of each one are going to be left? The one that is not u at that point needs to be even after you separate the du. Does that make sense? Okay. So on the next one, if we do u equals secant, du is secant tangent. That leaves 5 tangents and 6 secants. But if u is secant, we don't care about secant. The fact that there's 5 tangents, that's bad because it's odd. If u is tangent, du is secant squared. So then we separate out 2 secants. that leaves 5 secants and 6 tangents. But if u is tangent, the fact that there's 5 secants, that's bad. So neither approach works well here. And we would use something called a reduction formula in a table or something like that, or have to be really creative to get this problem to work out. Okay. All right, so neither approach works well. On number 5, if u is secant, du is secant tangent. There's no way to get tangent, or there's not an easy way to get tangent, and so then that's not a good approach on this problem. If u is tangent, du is secant squared. After we separate out secant squared, there's 4 secants. The fact that that's even is good because u would be tangent, and so u equals tangent is going to work on problem 5. Does that make sense to everybody? All right, on problem 6, u equals secant doesn't work because du is secant tangent, and there's not a good way to get tangent. If u is secant, du is secant squared. That leaves 1 factor of secant. The fact that that's odd is bad, and so neither approach works well on secant cubed. And so that's one where you have to be pretty creative to get that one to work, and that's one I actually would like you to try on the homework. I think I put it on the WebAssign. If not, it's on a worksheet in the shared drive. That's one worth trying to do. Okay, so we should for sure try that one. But there's not a consistent technique when neither one works. Any questions on those first 6? Does everybody follow what we're talking about? Okay. Now for sine and cosine, the same thought process works. We just had a quicker rule. But the idea is, if we think it through the way we're thinking it through now, on the first one, if u is sine, then du is cosine. And so there'll be 2 cosines left after we separate it, 2 cosines and 5 sines. We don't care about sine, but the fact that there's an even number of cosines means this is going to work. If u is cosine, du is negative sine, so you have to get a negative, but after you separate that out, you have 3 cosines, which we don't care about, but we have 4 sines, which we do care about. The fact that there's going to be 4 left means this is going to work. So both work in this case. On the next one, if u is sine, du is positive cosine. So if u is sine, du is cosine. That leaves 4 cosines. We can rewrite that easily in terms of sine, so that works. If you let u equal cosine, du is negative sine. There's not a good way to get sine because it's not there. And so u equals sine is the only one that works here. On the next one, if u is sine, du is cosine. After splitting off a cosine, there's only 1 cosine left. The fact that u is sine means that that odd power is bad, so u equals sine doesn't work. And same with cosine. If u is cosine, du is negative sine. We'd leave 1 sine and 2 cosines. If u is cosine, we care that there's 1 sine. That's bad because it's odd. So neither one works well here. On this one, it's u equals sine. On this one, it's u equals cosine. And on this one, it's neither. We talked about these last week. We can think them through like sine and cosine, but the quick rule is that if one of them has an odd power, let u equal the other one. That's why they both work here, because they both have odd powers. This has an odd power, so u is sine. Here, neither of them have an odd power, so neither approach works well. For sine and cosine, when neither one works well, there is a consistent strategy. What do you do when neither one works well over here? What do we use for those? What do you guys think? So we have those half angle formulas that we can use for those. So when they're both even to start with, we use half angle. On the left for secant and tangent, when neither works, there's not a consistent strategy. It's not the same from one problem to the next. Okay, any questions at all on this? Everybody good? Okay, so I want to look at one where neither approach works. I want to talk about 2 problems where neither approach works. But we've done one a lot already, and then the other one we have not. So again, we're talking about powers of secant and tangent. Neither u sub approach works well for either of these problems. So like if you let u equal tangent on this first problem, du is secant squared, well, we can't get that. And if you let u equal secant, du is secant tangent, and we can't get that either. Who remembers what you do for this integral? So this is the one I don't want to work all the way because you've done it a bunch.
Sine over cosine.
Yeah, so we rewrite this as sine over cosine, and then we do a u sub where u is cosine x. And so it's pretty straightforward once you're there. Cotangent would be almost the same, except it'd be cosine over sine. Does that make sense to everybody? Okay, and now secant, we've not done this problem. And none of the approaches we've talked about works well. And so this is one of the ones where up here we're talking about neither one works. And so there's not a consistent approach. And we have to try to figure out something that would apply here. What you end up doing for secant is you think of it as secant x over 1. And you multiply by secant x plus tangent x over secant x plus tangent x. Now that's real weird. But before we talk about why I would do that, I want to talk about why I'm allowed to do that. So why is this step, maybe it doesn't make sense why we would want to do it, but why is it okay to do it? What am I actually doing?
Because you're just multiplying by 1.
Yeah, so I'm actually just multiplying by 1. Like secant is obviously the same as secant over 1. And then this over itself, that's just 1. So multiplying by that is allowed. Now, the reason you do it is because if I now distribute the top, I get that on top and I get this on bottom. And now look closely at what's going on and see if you can figure out what we should do next. What do you guys think? Any ideas? So it's actually easy from here. It's maybe hard to see it, but it's easy from here. So there's something easy I can do to do this integral.
Do you factor out the secant on the top?
You don't do that, but you could. That would get us back up here.
U equals secant.
U equals not just secant.
Can you separate them? Or?
You could, but you don't want to. What's the derivative of secant? We know that. What's the derivative of secant?
Secant x tan x.
Okay, and what's the derivative of tangent?
Secant squared.
That sounds a lot like what's up here. So what could we do? So what if u equals secant x plus tangent x? Then what's du? So what's the derivative of secant again? Secant x tangent x. And the derivative of tangent is secant squared x. So why is this going to make it easy?
Because that's the numerator.
That's the numerator. So this is 1 over u du. Does everybody see that? So it's already the way we want it. This is already 1 over u du based on this substitution. Does everybody follow that? So now the integral of 1 over u du is natural log absolute value of u plus c, and that's natural log absolute value of secant x plus tangent x plus c, which is the answer. And so somebody figured out that if you do this, you happen to get the derivative of the bottom on the top. I did not come up with that. I had to look at some point a long time ago, probably. but this works out because you end up with 1 over u du. Questions on that? Now, cosecant x would work almost exactly the same way. And so now we are able to do all 6 basic trig functions. We're able to take their antiderivatives. Antiderivative of sine and cosine are both basic forms. Antiderivative of tangent and cotangent are done this way. Antiderivative of secant and cosecant are done this way. Does that make sense? All right, any questions so far? Okay, now we're gonna do something weird, weirder than what we've been doing. So I'm gonna put 4 or 5 or maybe even 6 algebra problems on the screen, and I'm gonna number them, and I'm gonna do at least one of the problems correctly, and I'm gonna do at least one of them wrong. And I need you guys to figure out which one or which ones are right and which one or which ones are wrong. So at least one will be completely right and at least one is wrong. And you guys got to figure out which ones. So, all right, so I'm going to put several on the screen. Nope, not integral. Man, I keep writing integral. Definitely don't need integrals on this. All right, am I allowed more than 6? All right, so 7 of them. So at least one is right. At least one is wrong. Let me know what you guys think.
Is 6 wrong?
Is 6 wrong? 6 is wrong.
Is 2 wrong?
2 is also wrong. Okay, why are 6 and 2 both wrong?
Because if you were to square them, you'd have to FOIL them and it wouldn't end up like that.
Exactly right. So if you square x plus 4, you don't get x squared plus 16, or at least not if you do it right. You get x squared plus 8x plus 16 because you have to distribute it all the way through. Does that make sense to everybody? And same thing over here. So the point on 2 and 6 is that you cannot take the square root of both parts when it's addition and subtraction. Does that make sense to everybody? Okay, what about when it's multiplication and division? Can you take the square root of both parts? Or each part?
Yes.
Yes. So when you're doing square root and it's multiplication division, you can do that. So this one's right because the square root of 25 is 5. The square root of x to the 4th is x squared. It turns out that 2 other ones are wrong that are on the screen, but it's more subtle as to why they're wrong. Any idea of those last 3, 4, 5, and 7? 2 of them are right, and 2 of them are wrong, but it's subtle as to why.
7 is wrong.
7's right, but that's okay. Because 4 times 4 is 16, and x to the 8 times x to the 8, you add the powers, so that is x to the 16. And so that's actually worth thinking about, that when you take the square root of a variable, you divide the power by 2, you don't do the square root of 16. Not for x to the 16. That one's right, but then 2 of these are wrong.
Is 4 and 5 wrong? And I know 4 is wrong because that's technically 1 over 25 in the front, right? And then if you took the square root of that, that wouldn't give you 1, or what? I don't know. 'Cause it could be
No,
plus or
you're all
minus,
right. 4 is wrong, but 5 is right. So your idea about the 1 over 5, that's true. But you can rewrite this as 1/5 x, which is what I think you're saying, and that is right. But x over 5 is the same as 1/5 x. Anyone know why this isn't right? So okay, real quick, what is the square root of x squared? That's tricky. Easier question. And you can type this
Plus or
in.
minus x.
Yeah, okay, let's figure that out. So what is the square root of 25?
5.
Is it, okay, so who thinks it's 5? Who thinks it's -5? And who thinks it's plus or minus 5? I'm curious. Type in the chat, and I won't judge you if you're wrong. A, B, or C. Type in the chat which one you think is right. A is just 5, B is just -5, C is, or green, is plus or minus 5. Okay. Yeah, all right. So I'm seeing most people are putting C, and some people are putting just 5. No one's putting this one. Some people are putting A or just 5. Okay, if it's C, then do this problem. Okay, so if the square root of 25 is plus or minus 5, then this is 7 or -7. This is 4 or -4. This is 10 or -10. And this is 8 or -8. Now, that means you have to do this as 7, 4, 10, and 8. But you also have to do it as 7, 4, 10, and -8. And you have to do 7, -4, 10, and -8. And 7 and -4 and -10 and -8. And -7 and +4 and -10 and -8. And there are 16 answers to this problem. Does everybody get that? That if we do this, this then gets 16 answers. If I throw this in, now there's 32 answers. We could all get, there's 32 of us, 31 of us in here. We could all put something different and potentially still be right. Does that make sense, everybody? No, that does not make sense. Everybody clear? This cannot have 32 answers or math breaks. Clear? Doesn't work. Okay, so we decide that that is 5. That is not -5, and that is not plus or minus 5. That's 5. That's why if you had an algebra teacher and he or she was good, they should have flipped out let's do this. They should have been mad if you did this and said, okay, that's the answer, because that doesn't cover the answers. That's only one of the answers. There are 2. There's square root of 7 and negative square root of 7. That's why you have to put this, because if you don't, you only mean the positive one, whether that's what you think you mean or not. When you write it, you only mean the positive one. That's what that symbol means. Does that make sense to everybody? We have to agree on that, because if we don't, this has 32 answers and nothing makes sense. Clear? Okay, now I understand that that's confusing, but that's why you have to have this. That's a big deal in square roots. That's a big deal in inverse trig and a lot of stuff. But that means the square root of x squared is not necessarily x. It's also not plus or minus x. Why is it not necessarily x? When is it x? When is the square root of x squared for sure just x? If x is what?
Greater than 0.
If it's greater than 0, or technically greater than or equal to 0. So if x is positive or 0, then this is x. But what if x is negative 4? So if x is negative 4, then what that symbol's saying is the square root of negative 4 squared. Well, that's the square root of 16, which based on what we just said is just 4. So it's not x, it's the opposite of x in that case. Does that make sense? So the simplest way to write it is actually that. It's the absolute value of x. And so then that way, if x is positive, it's just x, and if x is negative, it's the opposite of x. Now, that means that this is technically wrong because we don't know whether x is positive or negative. If x is positive, this is right. But if x is negative, it should be negative 4x, or it should be the absolute value of 4x. Does that make sense? And same deal here. Why does it not matter on 5 and 1? Why would it not matter on 5 and 1? So this should be for absolute value of x, and this should be the absolute value of x over 5. Why not necessarily there?
Because they're to a positive, or not a positive,
Even power. Yes, and that's what somebody said in the chat too, yes. So the fact that this ends up with an even power, x squared can't be negative, right? X squared is positive or 0. X to the 4th is positive or 0. X to the 1st, not true. If this was x to the 3rd, we technically need absolute value. Now, what we're going to work on is not necessarily that. We're going to talk more about the absolute value thing later. But what I would like to be able to do is I would like to be able to take something like this and get rid of the square root. Now, we already talked about you cannot take the square root of both parts because of the minus, right? So if it's adding and subtracting, you can't take the square root of both parts. So what we're going to do is we're going to figure out a weird way to get rid of this. And so I'm going to go through it, what we're going to do to get rid of this square root. And at first it might not make sense, and that's okay, but just give me a minute and then we'll talk about it. So we're going to do something real weird, and we're going to decide to let x equal 4 over 7 sine of theta, okay? Now, if I do that, then this is the square root of 16 minus 49 times 4 over 7 sine of theta squared, okay? If I square this, because it's all multiplication and division, I just square each part. So I get 16 minus 49 times 16 over 49 sine squared of theta. Does everybody get what's happening? Not how I picked this, but once that's true, then do we understand that this is true? Okay. Now the 49s cancel. And now the 16s are the same, so I could factor that out. Does that make sense? Now, what's 1 minus sine squared the same as? In terms of another trig function.
Cosine squared.
Cosine trig. Yeah, so I can rewrite this as the square root of 16 cosine squared theta. And now somehow subtraction has become multiplication. So everybody see that? So now I can take the square root of both parts. So we know multiplication, I can take the square root separately. We should have an absolute value here. We'll talk about later why we can drop that. So it turns out that within the theory behind this, we know that cosine's positive. And so then we're going to drop the absolute value. But we'll talk about that probably on Wednesday as to why the absolute value drops. The times, we can take the square root of both parts. Does everybody understand what happened on each step once I told you this? Not how did I figure this out? Are we good on what happened on each step? Okay, I want to go through another one, and then we're going to talk about how to pick that. Okay, so on this one, again, I'm going to try to change the subtraction into multiplication, and I'm going to use trig to do it. So on this problem, I'm going to pick x to be 8 over 5 secant of theta. Okay. And now if I do that, I rewrite this and I get 25 times 8/5 secant theta squared minus 64. I square that, so I get 64 over 25 secant squared theta minus 64. The 25s cancel. The 64 factors out. Secant squared theta minus 1 is positive tangent squared theta. And now, aside from the absolute value, we can take the square root of that and get 8 tangent theta. So does again, everybody get what happened on every step? Okay, so I want to talk about how to figure this out. All right, we're going to use this, it turns out, a lot. How do you think I picked 4 over 7 here? So let me explain that, but everybody kind of watch what's going on the screen if you're not looking at it directly. So what I needed to have happen is I needed these coefficients to match up so that I would end up with 16. Does that make sense to everybody? And then down here, I needed these both to end up as 64. Well, if you're looking at this original problem, by plugging something in for x, you're able to manipulate the coefficient that's on the x. So I put a 7 in the bottom because I wanted to get rid of the 49. And I put a 4 in the top because I wanted to end up with 16. Does that make sense to everybody? Okay, so 7 in the bottom canceled the 49, 4 in the top got me the 16 that I wanted. Here on the next one, I was able to get rid of the 1 with x. So I can't mess with the 64, but I can mess with the 25. So I put a 5 in the bottom because I wanted to cancel the 25, and an 8 in the top because I wanted to end up with 64. Everybody clear? Now, for the trig function, the options are going to be sine theta, tangent theta, or secant theta. And we have, go ahead. Somebody's raising their hand. Go ahead.
Yeah, if it was like plus 64, can we still do that by just making that a like negative 8/5?
So good question. You can fix it. The negative doesn't fix it because you're squaring it first. But what does fix it is to use tangent instead of sine or secant. Does that make sense? Let me show you why. What's that?
The identity.
Because of the way the identity is. So the identities for these are that sine squared plus cosine squared is 1. And 1 plus tangent squared is secant squared. Now, because you're under a square root, you need to end up with a positive trig function squared. Okay, so you need to end up with positive cosine squared and positive tangent squared, or in some cases, positive secant squared. Well, the way these work, if these are the three options, so we're going to either be able to pick sine, tangent, or secant. If these are the three options, the idea is that 1 minus sine squared becomes positive cosine squared, which is what we just used here. That guarantees a positive trig function. Well, I knew from the beginning that I could factor the 16s out. Like I could get the coefficients to match and factor them out. And I knew there was going to be a 1 and then a trig function squared. And on this one, I knew there was going to be a trig function squared minus 1. Well, secant squared minus 1 becomes tangent squared. And it becomes a positive tangent squared. Does that make sense to everybody? Now, does the order on subtraction matter? So could I do it where it's sine squared minus 1? If I did, I would get negative cosine squared, which normally would not matter, but does matter in a square root. Does that make sense? So for subtraction, the order matters. For addition, the order does not matter. For tangent, it could be 1 plus tangent squared becomes secant squared, or I could reverse that. And tangent squared plus 1 would become secant squared. So these are the identities. These are manipulations of identities we already know. But looking at this, I know that by picking the right fraction, I'm going to be able to factor it out where everything there is a 1, or so in place of the constant, it's going to be a 1. In place of the x part, it's going to be a trig function squared. So I knew it was going to be 1 minus a trig function squared, which meant I wanted sine. Here, I knew it was going to be a trig function squared minus 1, so I knew I wanted secant. Does that make sense to everybody? Now, so then what I want you to try to figure out is on this problem, let's make it. Okay, so if I have the square root of 9x squared plus 4, take a minute and write down, and don't work the whole problem out, but write down what x should equal. So it should be a fraction and then a trig function, and check it with me in just a second if you're wrong. I'll give you a minute or so to do. Okay, so what fraction should we pick?
16 over 81.
Other way. Instead of squaring them, you want the square roots because you're going to square whatever you put. So instead of 16 over 81, it's going to be 2 over 3. Because the idea is we're going to cancel the 9, but I'm going to square the 3 first. Does that make sense? So I'm going to cancel. Okay. So I'm going to cancel the 9 and end up with 4. So we should pick 2 over 3. All right. And then once I factor them out, I'm going to end up with a trig function squared plus 1. Well, for addition, the order doesn't matter. So that could also be 1 plus tangent squared, which will be secant squared. So I pick tangent. And now let's work it out. So if I plug that in, I get 9 times 2/3 tangent theta squared plus 4. I square that and I get 9 times 4 over 9 tangent squared theta plus 4. The 9s cancel, so I get 4 tangent squared theta plus 4. The 4 factors out. And tangent squared plus 1 is positive secant squared. Then I can take the square root and get 2 secant theta because now it's multiplication. so the question in the chat is you pick secant. It does matter because 1 plus secant squared would not be equal to tangent squared. That's okay. Does that make sense? So you have to pick based on this. So when it's going to be 1 minus trig function squared, we need to pick sine. If it's going to be addition in either order, we need to pick secant. Or, I'm sorry, we need to pick tangent. And when it's going to be a trig function squared minus 1, we need to pick secant. Now, it turns out, and we'll talk a little more about that probably Wednesday, that anytime you pick sine, you could also pick cosine, but you could not pick the others. And anytime you pick tangent, you could also pick cotangent, but not the others. And if you pick secant, you could also pick cosecant, but not the others. So these are the 3 we're going to use, but on this one had to be tangent. So, okay, so I'm going to put several up, and I want to just figure out, not going through all of the algebra, but I want you to figure out what should you let x? Because this algebra within here is about the same every time. Is everybody kind of starting to see that? You might want to work one more if you have time before tomorrow, but before tomorrow's class. But let's just see if we can figure out what x should be. Give you guys another 30 seconds or so, and then we're going to go through these. Okay, so let's go through just what we should let x equal. So on the first one, we want to cancel the 9 and end up with 4. So we should pick 4 over 3 as the fraction. Is everybody clear why? Please ask if anything's unclear. That's good. Okay, and then we're going to end up with 1 plus a trig function squared. The one that ends up being addition in either order would be tangent. So we should pick 4/3 tangent theta, and then the math, like the algebra, will work a lot like this. Okay, on the next one, we want to get rid of the 2 and end up with 25. So I'm sorry, to get rid of the 4 and end up with 25. So to get rid of the 4, we're going to put a 2 in the bottom. To end up with 25, we're going to put a 5 in the top. After factoring things out, we're going to end up with 1 minus a trig function squared. This, on subtraction, the order matters. So then we should pick sine theta. Everybody clear how to pick that out? Any questions? Okay, for the next one, we want to get rid of the 25. So remember, it's not always the second one, it's the one with X that you're going to cancel out. So we're going to cancel the 25, which means we're going to put a 5 on the bottom. We're going to end up with 49, so we're going to put a 7 on the top. We're going to end up with a trig function squared plus 1. So we need to use tangent, because 1 plus tangent squared is the same thing as tangent squared plus 1, which is then secant squared. All right, so on addition, order does not matter. For subtraction, the order does matter. For the next one, we want to cancel 81 and end up with 121. So we put 9 on the bottom and 11 on the top. We're going to end up with a trig function squared minus 1, which means we should choose secant, because the order on subtraction does matter. So secant squared minus 1, not sine and not tangent. Any questions on those? Okay, now 9 minus x squared is just a special case of this. On this case, the coefficient of x is 1, so there's nothing to cancel, which means we want 3 or 3 over 1, but not 1 over 3. So either 3 or 3 over 1, but not 1 over 3. We're going to end up with 1 minus a trig function squared, so we should pick sine theta. For the next one, we want to cancel 16 and end up with 1. So we're going to pick 1/4. Again, we're going to try to get 1 minus a trig function squared, so we want sine. So subtraction and the order does matter. On the next one, we want to get rid of the 4 and end up with 25. So we're going to put a 2 on the bottom, a 5 on the top. We're going to end up with a trig function squared plus 1. So we're going to start with tangent and end up with secant squared. Next one, same idea. Nothing to cancel, and we want to end up with 49. So either 7 or 7 over 1. And again, tangent. Last one, we want to cancel the 25. So we put a 5 in the bottom. We want to end up with 1, so we put 1/5. And again, this one's tangent, because we're going to end up with tangent squared plus 1. Now, in tomorrow's lecture, we're going to be doing integrals that involve square roots like this. And on the problems we do tomorrow, the first step is going to be to pick this x and to use that x to get rid of the square root. So we need to be really, really comfortable, because there's a lot that follows this. And so this is real weird to start a problem, but we want to get real comfortable picking out the right coefficient and the right trig function. One other thing is, it does not have to be nice perfect squares. So if I end up with like 16x squared plus or minus 7, then okay, I want to get rid of the 16, which means I put a 4 on the bottom. I want to end up with 7. That means I'm going to put the square root of 7 and then secant theta, because it's secant squared minus 1. And the 16 doesn't have to be nice either. If that was 10, it'd be square root of 7 over square root of 10. So you don't need to have perfect squares for this to work. Most examples we do, they will be perfect squares, but in general, they don't have to. And so we just want to make sure that everybody's comfortable with this. That's actually it for today. But if you're unclear on any of these, please stick around and ask questions, because if we can't do this, it's going to be real tough tomorrow. All right. That's it for today. Thanks for coming, you guys. And I hope I'll see you tomorrow. Thanks.